Welcome to CyberXplain channel. Today we are going to discuss AI for security, your beginner's guide to machine learning and beyond. CyberXplain. Hey everyone, welcome. Today, we are diving into something super cool and increasingly important, artificial intelligence, or AI, and how it's shaping the world of security. You might hear these terms thrown around a lot, and it can feel a bit overwhelming, right? But don't worry, we are going to break it all down, step by step, like we are just chatting over a cup of coffee. Think of AI as your super smart digital assistant, constantly learning to help protect our systems and data. It's not just for science fiction movies anymore, it's a powerful tool in our cybersecurity arsenal. So, why exactly is it such a big deal for us in security? Because the bad guys are getting smarter, and we need to be even smarter. Let's kick things off with the big picture. What is AI? Imagine you have a really clever robot that can think, learn, and solve problems just like a human. That's the essence of artificial intelligence. It's a broad field focused on making machines mimic human intelligence. This means designing computer systems that can perceive their environment, reason, learn, and take action to achieve goals. Think about your voice assistant on your phone, or a self-driving car. Those are everyday examples of AI in action. It's about building machines that can be smart in different ways, from recognizing faces to playing chess. Now, if AI is the big umbrella, then machine learning, or ML, is a crucial part of what makes that umbrella work. Think of it this way. If AI is about making machines intelligent, ML is the method by which they learn to be intelligent. Instead of explicitly programming a computer for every single task, we feed it data and let it figure out the patterns and rules for itself. It's like teaching a child by showing them many examples, rather than giving them a rulebook. So, ML algorithms allow computers to improve their performance on a task over time without being explicitly programmed for every possible scenario. This self-learning capability is incredibly powerful for security tasks. You might also hear the term deep learning thrown into the mix, so let's clarify how these three relate. Think of it like a set of Russian nesting dolls. AI is the biggest doll, the overall concept of machine intelligence. Machine learning is the next doll inside, a specific approach to achieving AI by learning from data. And then, deep learning is the innermost, smallest doll, a very powerful type of machine learning. Deep learning uses special structures called neural networks, which are loosely inspired by the human brain, to learn incredibly complex patterns from huge amounts of data. We'll dive deeper into neural networks soon. But for now, remember, all deep learning is ML and all ML is AI. Alright, let's start with the most common type of machine learning you'll encounter, especially in security, supervised learning. Think of it like teaching a child with flashcards. You show them a picture of a cat and say cat, then a dog and say dog. You are providing both the input, the picture, and the correct answer, the label. The supervision comes from having these pre-labeled examples. The model learns by comparing its guesses to the correct answers and adjusting itself to get better. It's like a student with a teacher guiding them, always knowing what the right answer should be during training. This method is incredibly effective when you have a lot of historical, labeled data. So, how does this teacher's pet actually work? The foundation of supervised learning is having a dataset where every piece of information already has a correct answer or label attached to it. For example, if you are building a system to identify images of apples, your dataset would include many pictures, with each one clearly marked apple or not apple. This labeled data acts as the training ground for our AI model. The model looks at the features of each input and tries to associate them with the correct label. It's like giving a detective a bunch of solved cases, each with the crime scene details and the perpetrator's identity. The detective studies these to learn how to solve future cases. Once we have our beautifully labeled dataset, it's time for the training phase. The machine learning algorithm processes this data, making predictions based on what it's seeing. Initially, its predictions will likely be pretty bad, just like a beginner student. But here's the magic, it compares its prediction to the actual correct label we provided. If it's wrong, it learns from that mistake. It adjusts its internal settings, we call these weights and biases, to try and get closer to the right answer next time. This process is repeated thousands, sometimes millions, of times, constantly refining the model until it makes accurate predictions most of the time. It's a continuous cycle of prediction, error, and adjustment. After all that intensive training, our supervised learning model is ready to tackle new, unseen data. This is where it really shines. When you feed it a brand new input, something it has never seen before and doesn't have a label for, the model uses all the patterns and rules it learned during training to make an educated guess. For instance, if you trained it on those Apple pictures, and now show it a new image, it will confidently tell you if it thinks it's an apple or not. It's essentially applying its learned knowledge to classify or predict outcomes for new observations. This ability to generalize from past examples to new situations is the core power of supervised learning. Let's bring this to life with a super common example we all deal with: spam email. Ever wondered how your email provider filters out all those unwanted messages, often with incredible accuracy? It's largely due to supervised machine learning. The challenge is huge. Spammers constantly evolve their tactics, changing keywords, sender addresses, and even entire message structures. A simple rule-based system that just blocks emails with VIAG might miss the next wave of scams. We need something that can adapt and learn on its own. This is where AI steps in as our digital bouncer, deciding which emails get into your inbox and which go straight to the junk folder. So, how do we build an AI model to catch spam? First, we need data, and lots of it. This means collecting countless emails, both legitimate ones, which we call ham, and the actual spam emails. This raw data collection is the very first step. It's like gathering ingredients for a recipe. You need everything before you can start cooking. These emails come from various sources: users marking messages as spam, honeypots designed to attract malicious emails, and vast archives of communication. The more diverse and representative our email collection is, the better our model will learn to distinguish between the good and the bad. This is where the supervised part really comes in. Once we have a mountain of emails, we need to label each one as either spam or not spam, ham. This can be a labor-intensive but critical step. Think about how you mark emails in your inbox. You are essentially providing labels. Many email services use crowdsourcing for this, where user feedback directly contributes to the labeled dataset. This human-labeled data is the ground truth that our machine learning model will use to learn from. The accuracy of these labels directly impacts how well our AI will perform later on, so it's vital to get this right. With our labeled data ready, we can now train our model. The computer takes these emails and their labels and starts looking for patterns. It might notice that spam emails often contain certain keywords, weird formatting, or links to suspicious websites. For example, an email with a subject line like urgent. Win $1 million now is probably spam. The model doesn't understand these words like we do. It converts them into numerical features. It learns to associate these features with the spam label. It's an iterative process, where the model constantly adjusts its internal logic to minimize classification errors across the entire dataset. Once our model is trained, how do we know if it's any good? We use a separate set of labeled emails, called the test set, that the model has never seen before. We let the model classify these emails, and then we compare its predictions to the actual labels. Did it catch most of the spam? Did it accidentally flag important legitimate emails as spam? We look at metrics like accuracy and false positive rate to understand its performance. If it's not performing well enough, we go back and fine-tune it, maybe collect more data, adjust the algorithm's settings, or try a different approach. This evaluation is critical before deploying the model. Finally, if our model passes all the tests, it's deployed into the real world to start protecting your inbox. This means integrating it into the email server infrastructure, like Microsoft 365 Exchange Online or a custom mail system. But the job isn't done. Spammers are always finding new ways to bypass filters, so the model needs to continuously learn and adapt. It's common for models to be retrained periodically with new, freshly labeled data to keep up with evolving threats. This ensures that your email filter remains effective, catching the latest spam attacks and keeping your inbox clean. It's an ongoing battle, and our AI is on the front lines. Now, let's switch gears to another fascinating type of machine learning, unsupervised learning. Unlike supervised learning, there's no teacher or labeled data here. Instead, you just give the model a bunch of raw data, and its job is to find hidden patterns, structures, or relationships all by itself. Think of it like a detective without any solved cases, just a pile of crime scene photos. The detective has to group similar photos together or identify unusual ones, trying to make sense of the chaos. This is perfect for situations where you don't have labels, or where the patterns are too complex for humans to easily spot. It's about letting the data speak for itself. So, without labels, how does it learn? Unsupervised learning algorithms look for inherent structures within the data. One common technique is clustering, where the algorithm groups similar data points together. Imagine you have a bunch of customer profiles, and without knowing anything about them, the algorithm might discover groups of customers who behave similarly. Another technique is dimensionality reduction, which simplifies complex data by finding the most important underlying features. It's like finding the main themes in a really long book without being told what they are. It helps us discover insights and anomalies that might otherwise be hidden in vast datasets. Unsupervised learning is a powerhouse for security teams, especially for anomaly detection. Imagine your network traffic. It's a constant stream of data with no normal or attack labels. An unsupervised model can learn what normal network behavior looks like, typical data volumes, common ports, usual communication partners. Then, anything that deviates significantly from this learned normal is flagged as an anomaly, potentially indicating an intrusion or malware. It's also great for grouping users with similar access patterns in an identity system, helping identify suspicious privilege escalations. Think of it as a vigilant watchman who learns the daily routine and immediately notices anything out of place. Now for our third type, reinforcement learning. This one is really interesting and quite different from the others. Think of it like teaching a dog tricks using treats and scolding. The agent or AI model interacts with an environment, takes actions, and then receives rewards for good actions or penalties for bad ones. It learns through a process of trial and error, figuring out which actions lead to the biggest cumulative reward over time. There's no labeled data and no direct supervision. The learning comes from the feedback loop with the environment. It's like a child learning to ride a bike. They fall, they get up, they try again until they master it. This is how AI learns to play complex games or control robots. The core idea in reinforcement learning is defining a reward function that guides the agent. When the agent performs an action that brings it closer to its goal, it gets a positive reward. If it moves further away, it gets a negative reward or penalty. The agent's goal is to maximize the total reward it receives over time. It tries out different strategies, observing the outcomes, and gradually building a policy, a set of rules for what action to take in any given situation. Imagine a game where picking up a coin gives points and falling off a cliff subtracts points. The AI learns to navigate the world to get the most points. This continuous feedback loop drives the learning process. Beyond mastering complex games like chess or Go, reinforcement learning has some exciting applications. It's used to train robotic arms for manufacturing, or even to optimize energy consumption in data centers. In security, while less common today, its potential is huge. Imagine an AI agent learning to navigate a simulated network environment, trying to find vulnerabilities or defend against attacks. An AI could learn optimal patching schedules, or even how to automatically configure firewalls in response to emerging threats. It's still an active research area in security, but the idea of an AI proactively learning to secure systems through experimentation is very compelling. Okay, let's shift gears again and talk about something really cool, natural language processing, or NLP. Have you ever talked to Siri or Alexa, or had your email flagged for weird grammar? That's NLP at work. It's a branch of AI that gives computers the ability to understand, interpret, and generate human language. Our regular human language, with all its nuances, slang, and sarcasm, is incredibly complex for a machine. NLP aims to bridge that gap, allowing computers to process text and speech in a way that's meaningful. For us in security, this means we can make sense of mountains of unstructured text data like security logs, threat reports, or even phishing emails. How do computers start to understand our language? It begins with breaking it down into smaller, manageable pieces. First up is tokenization, which means splitting a sentence into individual words or tokens. So, hello, world becomes hello, world. Next is normalization, where we clean up these tokens. This might involve converting all words to lowercase, removing punctuation, or reducing words to their base form, example, running, ran, runs all become run. This standardization helps the computer recognize that different forms of a word actually mean the same thing, making the analysis much more consistent and effective. Once we have our clean tokens, how do we turn them into something a computer can actually process numerically? This is feature extraction. A simple method is bag of words, where we just count how often each word appears, ignoring grammar or word order. If malware appears 5 times, that's a feature. A more advanced technique is word embeddings, which represents words as dense vectors of numbers. Crucially, words with similar meanings are mapped closer together in this numerical space. This allows the model to understand semantic relationships that attack and breach are related, for example. These numerical representations are what our ML models then use to find patterns in text. So, how do we use NLP in our security world? One powerful application is sentiment analysis. This involves determining the emotional tone behind a piece of text. Is it positive, negative, or neutral? In security, we can use this to scan social media, forums, and dark web discussions. If we see a surge of highly negative sentiment around a particular software vulnerability, or unusually excited discussions about a new exploit kit, that's a critical piece of threat intelligence. It helps us prioritize which threats to investigate first, even before formal reports are published. We can proactively understand the mood of the threat landscape. Another massive application of NLP is in analyzing security logs from your SIEM, Security Information and Event Management system. Think about the sheer volume of logs generated by servers, firewalls, and applications in a large organization like yours. It's practically a fire hose of text. Manually sifting through these for suspicious activity is impossible. NLP can automatically parse these unstructured logs, extract key entities like IP addresses, usernames, and event types, and then identify unusual patterns or specific attack signatures. It transforms raw, messy log data into structured, actionable intelligence, making our SOC analysts' jobs much more manageable. Remember our spam detection example? NLP takes that to the next level for phishing. It doesn't just look for generic spam keywords, but understands the asterisk intent asterisk and asterisk context asterisk of an email. An NLP model can analyze the writing style, grammar errors, urgent language, and suspicious links within an email to determine if it's a carefully crafted phishing attempt, even if it mimics a legitimate sender. For example, it can spot subtle differences in a domain name that a human might miss, or recognize that an email asking for password reset is unusual for a particular user. This provides a much more nuanced and effective defense against sophisticated social engineering attacks. Alright, prepare to have your mind blown. Let's talk about generative AI. Up until recently, most AI was discriminative. It tried to classify or predict based on existing data. Generative AI is different. Its superpower is creating brand new, original content that has never existed before. Think about how ChatGPT writes essays, or how AI can generate realistic images or even music. It's like an incredibly talented artist or writer who can produce new works based on what they've learned from millions of examples. This capability opens up a whole new world of possibilities, both amazing and a little bit scary, especially for us in security. So, how does a machine conjure new things out of thin air? Generative AI models learn the underlying patterns and structure, the DNA, of the data they are trained on. Imagine feeding an AI millions of pictures of cats. It doesn't just memorize them, it learns what makes a cat, the fur, the whiskers, the eye shape. Once it understands these underlying characteristics, it can then generate a new cat picture that looks perfectly plausible, even though it's never seen that exact cat before. It essentially learns how to speak the language of the data it's given, whether that language is images, text, or code. The most widely known application of generative AI right now is probably text generation. Tools like ChatGPT are prime examples. You can ask them to write an email, summarize a document, draft a poem, or even generate code snippets. These models have been trained on vast amounts of text from the internet, allowing them to understand context, grammar, and style remarkably well. They predict the next most likely word in a sequence, building coherent and relevant sentences, paragraphs, and even entire articles. This capability is rapidly changing how we interact with information and automate creative tasks. But generative AI goes far beyond just text. It can generate incredibly realistic images from text descriptions. Imagine typing an astronaut riding a horse on the moon and getting a stunning image back. This is done by models like DALL-E or Midjourney. And for us technical folks, it can also generate code. Give it a description of what you want a function to do, and it can write the Python or JavaScript for you. This is an enormous productivity booster, automating boilerplate code or helping developers quickly prototype. The ability to create visual and programmatic content opens doors we couldn't have imagined just a few years ago. Now, let's talk about the dark side for a moment. Just as generative AI can be used for good, it can also be weaponized. For red teams, the ethical hackers who simulate attacks, generative AI is becoming a powerful tool. It can create highly convincing phishing emails, customized for specific targets, with perfect grammar and context, making them incredibly hard for humans to detect. It can also generate realistic fake data for social engineering or even assist in crafting novel malware variants by suggesting code snippets that bypass traditional antivirus. This is why understanding its capabilities is crucial for our defense. But don't despair, blue teams can harness generative AI too. One huge benefit is creating synthetic data. This is fake but realistic data that mimics real-world network traffic or user activity. We can use it to train our own security models without risking actual sensitive data or to test new defenses against simulated attacks. Generative AI can also process vast amounts of raw threat intelligence from various sources and summarize it into concise, actionable reports, saving analysts hours of work. It can even help us generate realistic decoy documents to trap attackers, making our defenses smarter and more adaptive. Let's take a quick peek under the hood at how some of these amazing AI capabilities are built, particularly deep learning. This brings us to neural networks. Don't let the name scare you, it's just a fancy term for a type of computer program loosely inspired by how our own brains work. Imagine a network of interconnected neurons, simple processing units. Each neuron takes some inputs, does a little calculation, and then passes its output to other neurons. When enough neurons fire in a certain way, it triggers an action or a recognition. It's a way for computers to learn complex patterns by building layers of these simple connections, mimicking how our brains identify faces or understand speech. So, what makes a neural network deep? It simply means it has many layers of these interconnected neurons. Think of it like a chain of command, where each layer learns something a bit more complex than the last. The first layer might detect simple edges in an image, the next might combine those edges into shapes, and a deeper layer might combine shapes into specific objects like a face or a car. The more layers you have, the more intricate and abstract patterns the network can learn. This deepness allows deep learning models to handle highly complex tasks, from recognizing speech with high accuracy to powering generative AI models. The real power of deep learning comes from its ability to perform hierarchical feature learning. This means it doesn't need humans to tell it what features to look for, like is there a suspicious link? Instead, it discovers these features by itself, layer by layer, from the raw data. In an image recognition task, for example, early layers learn to detect basic lines and corners. Middle layers combine these into parts of objects, like an eye or a wheel. Finally, the deepest layers combine these parts to recognize complete objects, like a human face or a vehicle. This automatic feature extraction is what makes deep learning so effective for tasks where features are hard to define manually. Now, let's bring it all back to how AI is practically used to make our lives easier in IT and security operations. One of the biggest impacts is in the Security Operations Center, or SOC. Imagine the constant barrage of alerts. AI can automate the first line of defense, triaging alerts, filtering out false positives, and correlating related events across different systems. This isn't about replacing human analysts, it's about empowering them. AI handles the mundane, repetitive tasks, allowing our skilled analysts to focus on complex investigations and strategic threat hunting. It drastically improves efficiency, reduces alert fatigue, and speeds up incident response times. It's our digital assistant for the SOC. AI also excels at user behavior analytics, or UBA. Think about the daily actions of all your employees. An AI model can establish a baseline of normal behavior for each user, what files they usually access, which applications they use, when and from where they log in. If an employee suddenly starts accessing unusual files, downloading large amounts of data late at night, or trying to log in from a strange location, the AI flags it. This is incredibly powerful for detecting insider threats, compromised accounts, or even subtle signs of privilege abuse that might go unnoticed by traditional rules. It's like having a smart detective constantly monitoring everyone's digital footprint. Beyond detection, AI can assist with proactive security tasks like vulnerability management. Instead of just scanning for known vulnerabilities, AI can analyze your network's topology, existing security controls, and recent threat intelligence to predict which vulnerabilities pose the highest actual risk to your specific environment star. It can prioritize patching efforts, suggesting which systems need immediate attention based on exploitability and potential impact. Imagine an AI sifting through thousands of CVEs and telling you exactly which 10 are most critical for your company to fix right now. This shifts us from reactive patching to truly risk-driven remediation. As powerful as AI is, it's not a silver bullet, and it comes with its own set of security challenges and pitfalls. Attackers can try to poison our models during training by feeding them bad data, causing them to make wrong predictions. This is called model poisoning. Or they might craft inputs specifically designed to evade detection by a trained AI, known as adversarial attacks. Another challenge is explainability. Sometimes it's hard to understand why an AI made a certain decision, which is crucial for auditing and trust. So, best practices include securing training data, robust testing against adversarial examples, and striving for transparent, auditable AI systems. We need to secure the AI itself. We've covered a lot today. From the basics of AI and machine learning to the fascinating worlds of NLP and generative AI, and how it all comes together in security operations. I hope you now have a clearer picture of how these powerful technologies work and why they're so vital for us. Remember, AI isn't just a buzzword. It's a fundamental shift in how we approach cybersecurity challenges. By understanding its capabilities and limitations, you are better equipped to leverage it for defense and mitigate its potential for attack. Keep exploring, keep learning, and stay curious. Thanks for joining me on this journey, and I'll see you next time. Thanks for watching. Subscribe to the CyberXplain channel. See you on the next video.